Okay, so now we're going to get into some of the math behind rotation transformations. You don't necessarily have to really know this stuff on a daily basis. Even, people who've been writing engines for years don't really work at this level. But to have an understanding of where this math comes from and why it works, it's really valuable. And so we're going to go into understanding how these transformations work in the various dimensions that we may be doing them. So let's kind of jump into it. Cool. So we are used to already doing rotations in the xy plane with two-dimensional vectors. No matter what we do, we're still going to be in the xy plane. And so now we want to take that information, that knowledge, and move it into the third dimension. Right, as we know, the xy is represented by a column matrix, column vector of xy with a 0 in the z position. But if now we have a z position, how do we do that? So let's start with this point on the xy plane, which is clearly has a 0 component for y, and we want to now rotate it by theta. The resulting point, right, will be the position, the value of cosine theta times the x, and then also sine theta times y. That's going to be the value that we anticipate having. So, well, sorry, not times y, but yes. In this case, I don't believe. Well, our y value is going to be 0, so I think this is incorrect here because 0 times anything is going to be 0. The value that we care about here is actually it's going to be cosine theta times x. Yes, because x is our magnitude from prior. I'll correct the slides maybe later, but it's going to be times r, and r being the magnitude of the point, in this case x. So it'll actually be sine theta times x, cosine theta times x as well. Anyways, probably like a minor typo. Moving on. And so if we were to instead move the entire basis of the thing, right, we would still have a value that is equivalent to 0 on the x prime axis. And so if we were to rotate the whole thing, you can kind of imagine that if we had a position in y, we rotate it that way, we'd see the same thing kind of on the y-axis. So, basically, to get a 2x2 matrix for rotation, as we can see, it's cosine theta times x, the x value, and then negative sine theta times the y value, and sine theta times the x value, and cosine theta times the y value for the y. And you can kind of see where that comes from, where, when we rotate it here we have cosine sine to give us the x, and here we have cosine negative sine, or it's negative sine cosine. And that's going to give us the y. And so you can see the two column matrices they're lining up with that. Yes. Sort of cosine sine, and then opposite would be cosine negative sine. I'm not sure if I'm explaining this particularly well, but when you do the matrix math and the derivation of this, I think you'll get to this realization where to get the x position, right, it's cosine theta times negative sine theta plus negative sine theta of y, and then to get the y, it's sine theta plus cosine theta of x, which would cover us in both cases. So let's look at some common rotations on z. If we do a rotation of 0 degrees, we get the identity matrix, which is what we expect to see. If we do a rotation of 90 degrees, then we get this value, which will basically kind of flip things around. So if you can kind of see the first row, 0, negative 1. So what we're going to get is negative y in place of the x value for x, and then the x value for the y. So we're going to get a value of xy is going to turn into negative yx. So we've sort of created the reciprocal. Then a rotation of 180 degrees is simply going to give us a negative identity, or like negative. And the 270 is going to be the negative version of that flip we talked about. And so what we're going to get is a y and negative x. And so you can kind of see how these things sort of figure out from the rotations and give us exactly what we expect. So to turn this into a 3D rotation in only the z-axis, it's actually pretty straightforward. We just kind of add this, like we just put it into an identity matrix, right? Because here z is going to maintain its value always, with the column and the bottom row, the final column and the bottom row being 0, except for the 1 in the diagonal. So what we're going to do is we're going to rotate x and y values and mess around with that, but the z value is always going to kind of turn into the same thing that we expect. So yeah, if we do the same kind of concept in x, we will see we get a very similar equation in x, but we keep the x value stagnant, just like we did in the z-axis. In fact, if you'll notice, cosine, negative sine, sine, cosine, the exact same values in the same order as the z, right? Cosine, negative sine, sine, cosine, cosine, negative sine, sine, cosine, same thing. So now when we go into the y, it's the same, but we have to keep y the same, which kind of creates this, that we keep the one diagonal and then we split it out. And you can see the y value will be kept constant at all times. However, it's still cosine, sine, negative sine, cosine, and so we'll still get the flip-flop of the x and z parameters. And so now you'll always be in the same plane. So some ideas, right? Like if we do a 90-degree rotation over y, you can see how that turns into exactly what we expected. Compare this to the z plane, where we had a negative 1, 1 in the x and y respective positions, and here we have it in the z and x positions, in the same way that you can see in the z example below. So some basic rotations, you can actually combine them, right? You can take a y rotation and a z rotation, and you can composite it down, and you can get a more sort of arbitrary rotation where this final matrix of 1, 1, you'll notice there is no diagonal at all. It's doing some pretty kind of unexpected stuff, but it works, which we'll see kind of how that happens later. And same thing in other combinations. So you can kind of combine rotations however you'd like. Now keep in mind that about the 0, you will be able to kind of do this order independent, right? Like if I rotate this up and then down and then to the right and then to the left or whatever, it's still going to end up in the same place. However, the order of matrix multiplications does matter per point, and if you're not around the 0 position. So if this object was over here and you moved it up, left, right, the ordering of those does matter, because right now we're in the 3x3 matrix, so rotation only. But if you were in 4x4 and you had a translation in there, you're not guaranteed that order independent behavior. So yeah, like I was saying, the order isn't the same, but for the most part, you will see very similar stuff. Right, but keep in mind, it's not always. Basically, matrices the order matrix multiplications, you have to take it into consideration. It's not always going to work. Okay, so let's talk a little bit about the Rodriguez rotation formula. So Rodriguez was a mathematician back in like the late 1700s, and he came up with a formulation to effectively create any arbitrary rotation for a matrix in matrix form, any arbitrary rotation transformation. This is quite heavy, this particular form of the equation doesn't really give you much of an idea of what's going on. But we'll kind of dig into that over the next few slides. And if you want a lot more information about this formula, the Wikipedia is a terrific place to look. But we're kind of going to dig into this and show how this works. So to kind of dig into it, the I in this equation is the identity matrix, and the theta is the amount around which you want to rotate a particular vector by another vector. And so what's important here is that the Rx is the cross product matrix of the two vectors. You have one vector you want to rotate, and then you have another vector that you're rotating about it. So imagine like drawing a vector in space, and then you're rotating around that vector, and that's how this thing works. And so the R is that vector, but the R bracket X is the cross product matrix, which we'll explain in a minute. And so R needs to, in this case, for this to work, the R needs to be a unit vector. So the magnitude of the vector, it needs to be normalized, otherwise you're going to get some funky effects. So to kind of talk a little bit about the final bit, the R cross R is effectively its tensor product, or its own cross product, effectively. Just the tensor product, which has a pretty straightforward value here, right? You're just taking the vector and multiplying it by its transpose, and you get the square down the diagonal and the kind of respective combinations. And then to talk about what this cross product matrix looks like, the Rx is, imagine the cross product of K cross product V. And so if you think about K cross V as the respective values in a vector, and then you look at it, it looks like, Kx Vz minus Kz Vy, blah, blah, blah. And if you pull out the matrix that you would need to get to that matrix, so imagine this value times K times V, this is the matrix here that would you'd multiply V by to get that cross product. So it's imagine like if you've taken a cross product of two vectors and turning it into a matrix. So if you multiply a particular vector by that matrix, you'll get the cross product. And so what's nice, if you look at it, it's a skew symmetric matrix, meaning that the transpose is also the negative, which is kind of a unique matrix. So if you multiply this by -1, you will get the transpose, which is pretty wacky, but also very interesting property. So going back to the formula, let's kind of break this down and kind of look at it into components. So we have this large equation. This is sort of what it breaks down to if you do all the math, and this is what it decomposes to. So let's define a couple of values. Let's set t to 1 minus cosine theta. Let's set c to cosine theta. That's nice. And s to sine theta. And so hopefully this will simplify this equation a fair bit. And so now we can look at it and see, okay, c plus xr squared t. It's a little bit more manageable. Yeah. And so now r is going to be this more simplified formula. You can see the sort of different column components. And if we add to this particular matrix, so at this point you can do this, right? You know what your vector is, you know what your everything is. If you were to multiply this by a vector, it would rotate about a particular vector in space. If you wanted to add to that translation, you would do it this way. You would add the fourth dimension to your matrix, and or you can multiply the previous one with the 1 and the diagonal of the W component and multiply it by translation, so that would work as well. And so let's kind of go and dig into it a little bit more and kind of see a couple of examples and work through how we would actually use this in practice. So you can see this complicated equation, although once you code it out, You don't need to ever do it again. We simplify it down and kind of distill it down to the different components. And so let's take a look at the diagonal specifically, because the diagonal looks quite similar, right? We've got basically just that cosine value plus the t value, which is 1 minus cosine, right? Plus the times the respective component to the power 2. So if we take that and we use that and kind of get the value for it, we can see that that value is going to be 3c plus t times the the squared, the magnitude of the vector to the but the power 2, because we're not taking the square root of it. This is because this particular x, y, and z is the unit vector that represents the axis of rotation. So like per the previous things, you can kind of imagine that this vector is what is the vector that represents where we're rotating. So that's kind of cool. And if we take a kind of a deeper look into this, we can see that if we break this down a bit further, x squared plus y squared plus z squared should be 1, right? Because it's a magnitude 1 vector. And so we can see that this can break down further into 3c plus t, but in this case t is just 1 minus cosine theta, right? So going further, we now have 2 cosine theta plus 1 is equal to this value, which is going to be the sum of these 3 of the diagonal. And as we kind of break it down, we see that cosine theta is equal to this value minus 1 divided by 2. And if we multiply both sides by this, but by the inverse, by the arc cosine or whatever, we can see that the theta is going to be equal to the inverse cosine of this value divided by 2. So using this, we can kind of figure out what actually the theta, the rotation amount, is as well if we just have access to the diagonal. There's like a lot of really cool parameters that are nice here. Like imagine you have a arbitrary rotation matrix in your object that you're using in your engine, and you don't know what the orientation is. You want to know. It's a big matrix and it's a blob of info. So how do you figure out the information relative to that? Well, one thing you can do is you can take a look at the diagonal of your matrix, figure out the vector of rotation, and also the theta of rotation about that vector. And this actually is really important and useful when you're building an engine, because you're going to always have to deal with okay, I'm going to use a quaternion to a rotation matrix and a rotation matrix to a Euler thing, and it's like you're always bouncing them around for some reason. So having different ways to manipulate, reach into a rotation matrix is actually quite effective. So let's go pop up again. You can see the first kind of component of the Rodriguez rotation formula is just the identity times the cosine theta plus the skew symmetric matrix times the sine theta plus the tensor product of our respective vector and the theta around that. And so as we kind of dig into that, right, we can see that to get the what are we doing? What is this doing here? I'm not really. Okay, I see. So in this case, if we take our Rodriguez matrix, our rotation matrix, and we subtract from it our transposed version, you can kind of see that the cosine identity and the r times r, they go away because the transpose of those, if you take a look, is going to be the same, right? XR, and especially in the tensor product, I think that's obvious, where you have XR, YR, XR, YR, that it's its own transpose. The tensor product is its own transpose. So those go away, and what you're going to be left with is 2 times the 2 times the skew symmetric matrix and sign, because when you transpose those, you get the negative version of that, so you just add. And what's really cool about that is now you can sort of figure out the XR of the vector. Again, this is sort of like being able to understand from just the skew symmetric matrix what our effective vector of rotation is. And so in this case, the XR is going to be just if we can get that matrix out of there, the second and third point in our rotation matrix minus the 3 and 2, the transpose divided by 2 sine theta, and then we can get the vector of rotation out of that in that way. So a bit roundabout explanation. I know if you guys need more depth into this particular slide and more information about this, please ping me on the Discord or email me. So I'm not explaining this particularly well, but this is just in one more way to extract from this formula what your rotation vector is. Okay, so let's go through a couple of examples. In practice, right, most of the time you're going to be using this at the highest level, so this is kind of showing you how you would do that. So say we have a rotation of 90 degrees over 0, 1, 0, and so we're rotating 90 degrees over the y vector. So we would then get a rotation matrix from the GLM in this case, right? With start off with identity matrix, 90 degrees about the y vector. And the rotation y that you're going to get in return is going to be this matrix, right? 0, 0, 1, 0, 1, 0, negative 1, 0, 0. We've seen this matrix prior. And so if we wanted to kind of see kind of what we saw in the previous slide, if we take the inverse cosine of the sum of the diagonals, which is 1 in this case, we'd have cosine of effectively 0, negative, like inverse cosine of 0, which is 90 degrees. Now if we wanted to do the same thing and with the vector, like the vector, we would take a look at our the second and the 2, 3 position minus the 3, 2 position, and the 3, 1 position, again, like as you can see in the slide. And in this case we see that XR is going to be 0, that YR is going to be 2 over 2 times 1, or 2 over 1, and ZR is going to be, the Z is going to be 0. And in this case, again, out of this rotation matrix, by using these formulas, we were able to figure out that the rotation vector of this particular rotation matrix is 1. So the Y vector. Here's another example, right? If we do the same thing, if we rotate do a rotation of 90 degrees about the sort of 1 vector, which is just pointing, 1, 1, 1. We can do the same equation for the diagonal, which is a bit more complex in this case, but still resolves to 1, and we get 90 degrees. And same thing we can do for the axis of rotation, which in this case we get 0.577 for each of the components, which is basically 1 divided by the magnitude, the square root of 3. There you go. Right. The reason that GLM will give you this better value, not 1, 1, 1, which is what we provided to it, is it normalizes that vector for you. And so that is the normalized vector. So yeah, pretty useful couple of things to have. And next I'm going to jump into another lecture that's going to talk a little bit about a little bit more rotation math in practice.